Okay, let's continue from where we left off last time. We were talking about polynomial functions. And we saw that polynomial functions are functions that can be written in this form. Oops. All the way down to we have all these terms of various different degrees of x, and the biggest degree, the biggest power of x is called the degree. I gave you names for some polynomials. Polynomials of degree 2 are called quadratic. Polynomials of degree 3 are called cubic, and so on. And I gave you some examples of different polynomials. We saw that if we had y equals, let's say, x cubed minus 3x, the graph of this function looked a lot like this. We know that it's an odd degree polynomial, so its ends go in opposite directions. We can see that the coefficient in front of the largest power of x is a 1. That's positive, so we know the right end goes up. We could easily figure out where this thing crosses the x and the y-axis. If I want to figure out its x-intercepts, we set y equal to 0. So we have x cubed minus 3x is equal to 0. We could factor that. X and x factors out. We're left with x squared minus 3. I guess that sort of factors. The x squared minus 3 is difference of squares, as long as you think of 3 as the square of the root of 3. So I could factor this as x times x minus root 3 times x plus root 3 equals 0. So this thing has zeros at x equals 0, x equals minus root 3, or plus root 3, and x equals minus root 3. So these three values where it crosses the x-axis are minus root 3, obviously 0, and plus root 3. And we can see that it has these two turnarounds, these places where we stop going up and start going down, and stop going down and start going up. So this has two turnarounds. And I gave you another example. I gave you y equals x cubed, I think it was plus 3x. And this one looked like this. This had no turnarounds at all. It's always going up. So it doesn't stop going up and start going down and then stop going down and start going up. It's always going up. And if you figure out where this thing crosses the x-axis and where it crosses the y-axis, you'll see that it only happens at x equals 0. So I have a question for you. Are there any cubic polynomials? Question?
Your question?
Okay, let me go. Are there any cubic third degree polynomials with exactly one term? Oh, it's third degree. You can't have more than two. Here's one with 0, and here's one with 2. Are there any with exactly one turnaround? So remember, well, actually, let me not give you that clue yet. So we see there's one with 2, and there's one with 0. Are there any with exactly one turnaround? Remember what you know about third degree polynomials. If there's one with exactly one turnaround, what would you be able to tell me about the ends of the function?
They'd be facing in the same direction.
Yeah, they either both go up or both go down. If I had one turnaround, so one turnaround like that, or one turnaround like that, either both ends would go up or both ends would go down. But we know that an odd degree polynomial has ends that go in the opposite direction. One end goes up and the other end goes down. So the answer is no, because one end goes up and the other down. Let's say I have a fourth degree polynomial. So there exists quartic fourth degree polynomials. Fourth degree, that's what quartic means. With 3 turnarounds. Shaped like say a W or an M, if you wanted to turn it upside down, and 1 turnaround. You know y equals x to the 4th, just have 1 turnaround. Shaped a lot like a parabola. Are there any fourth degree, so that's quartic again, polynomials with 0 or 2 turnarounds? We know they have at most 3 because it's fourth degree. 4 minus 1 is 3. You have 0 turnarounds or 3 turnarounds. Remember
Isn't it no because they both go in the same direction?
Yeah, because the ends both go in the same direction. If you had 0 turnarounds, the ends would have to go in opposite directions. Or if you had 2 turnarounds, the ends would have to go in opposite directions. But they go in the same directions. The answer is no. The ends have to go in the same direction. So the number of turnarounds of a polynomial of odd degree has to be even. And the number of turnarounds for a polynomial of even degree has to be odd. It's not something you have to memorize. You can work this out for yourself. You just reason this out for ourselves. So for an odd degree, it must be even. For an even degree, it must be odd. So for instance, if I had a polynomial of degree 20, it would have at most 19 turnarounds, but it couldn't have 18. It could have 17, but not 16, and so on. It could have any odd number starting at 19 and going all the way down to 1. A rational function is any function that can be written f of x equals g of x over h of x, where both g and h are polynomials. For example, say f of x equals, oh, let's say x minus 2 over x squared minus 3x plus 5. I have a polynomial of degree 1 on top. I have a polynomial of degree 2 on the bottom. Or let's say f of x equals 1 over x minus 2. I have a polynomial of degree 0 on top and a polynomial of degree 1 on the bottom. Even something like this. Oops. Just that's a polynomial, but I can write it as a rational function. It is a rational function also, because I can write it as x squared minus or plus 2x plus 5 all over 1. So one thing that should be clear to you is any polynomial is also a rational function. Now we've seen the kinds of graphs that polynomials have. They're smooth, you can draw them with no breaks. They have these turnarounds. The right ends and the left ends of polynomials either go up to infinity or down to minus infinity. Sometimes they go in opposite directions. Sometimes they go in the same direction. Rational functions can have features that polynomials don't. Then you know these. That was most of them anyway. Rational functions may have features that polynomials don't. For example, rational functions may have asymptotes. We'll talk more about asymptotes a little bit later in the course. We've already talked about them in pre-calculus. They don't necessarily have asymptotes, but they might. So for example, let's just do a few examples. Let's do a function you already know, y equals 1 over x. Y equals 1 over x. We already drew this one. It's a hyperbola. That's what that shape is called. It has a branch over here and a branch over here. And the x-axis happens to be what's called a horizontal asymptote. It's a line that the curve gets closer and closer to. And the y-axis happens to be a vertical asymptote. Again, it's a line that the curve gets closer and closer to. It's possible that your high school teachers gave you a definition for asymptote that isn't quite right. It's possible that they said that an asymptote is a line that the curve gets closer and closer to, but never crosses or never touches. That's not quite right. You can cross an asymptote. For instance, let's say I have x equals, let's say, x over x squared plus 1. We'll come, at this point, you don't have an idea really how to sketch this thing other than to plot a lot of points and connect them up. By later in the course, this will be relatively easy for you to sketch a graph of this thing. But let me just sketch it for you now. It looks a lot like this. Nice shape. Looks a lot like that. Where this is, of course, the x-axis. This is the y-axis. I'm sorry, that's the x-axis and that's the y-axis. My bad. This thing doesn't have any vertical asymptotes at all, but it does have a horizontal asymptote. The x-axis happens to be a horizontal asymptote. And you can see that we cross the x-axis right there. So you can cross a horizontal asymptote. Can't cross a vertical asymptote because then we'd have problems with it being a function. So we have these vertical asymptotes, these horizontal asymptotes. You even studied functions with slant asymptotes. So if I give you something like f of x equals, say, x, let's say, minus 1 all over, let's say, x. We'll make that x plus 1. This thing has what's called a slant asymptote. So you dot in the line, let's see, 1 plus. Oh, I'm sorry, that doesn't have a slant asymptote. Because I have to make the top degree 1 bigger than the bottom. That's better. So let's see this thing. that's a slant asymptote right there. And I think this thing looks like this. I have to do a little bit more work to check my answer, but I think it looks like this when we have this line y equals x that the curve gets closer and closer to. Yeah, that looks more or less right to me. So we can have these asymptotes. And again, we will talk more about asymptotes later. But, and this is sometimes given short shrift in high school, rational functions can also have holes. There's holes in the curve. So for instance, let's say I have f of x equals x minus 1 over x squared minus 1. This thing looks like this. It has a vertical asymptote of -1 at x equals -1. It has a horizontal asymptote of 0. We plug in, we can figure out where it crosses the x-axis. We plug in x equals 0, we get -1 over -1. So the y-axis crosses the y-axis at 1. But at x equals 1, if you try to plug x equals 1 in here, you get 0 over 0, and it's undefined. So this thing looks a lot like this. It has a hole in the curve right there. And for some reason, in high school, when rational functions are studied, you spend a lot of time on asymptotes, but little to no time on holes in the curve. I don't know why. Well, that's it. That's the study of all the preliminary material. Are there any questions before we move on? Looking for hands, for questions. Okay. Well, let's move on. The very first topic we're going to discuss is something called limits. And it's basically the idea of limit that makes the subject calculus. Limits, so this is section 1, 2 out of your textbook. So hopefully you have your textbook by now. Finding limits graphically and numerically. Again, we're using an old version of the textbook. The subject hasn't really changed since this, since this version came out. It's the new version is several $100s, and you should be able to pick up this old version for, probably less than 20. So let's go back to this function we were talking about here. So again, f of x equals x minus 1 over x squared minus 1. We already saw that this function has a hole in the curve at x equals 1. If we try to plug in 1 we get 1 minus 1 over 1 squared minus 1. That's 0 over 0. That's not defined. So f of 1 is not defined. That's why we have a hole in the curve. We can't plug in 1 in. But I have a question. What happens as you plug in values closer and closer to 1? So what do you get if you plug in x values closer and closer to 1? I'm going to ask you to pull out your calculator at this point. If you're using the calculator app on your phone, pull out your phone and bring up your calculator app. We're going to build a chart here. So on the top line, I'm going to have the x values. And on the bottom line, I'm going to have y values, which is just f of x. And right in the middle of the chart, I'm going to put a line here where 1 would be. We know we can't plug in 1. We get garbage. But we're going to plug in values closer and closer to 1. So imagine this is sort of the number line. Here is 1. And on the left, we'll plug in, say, 0.9, 0.99, 0.999. Those are numbers getting closer and closer to 1 from the left on the number line. And on the right, we'll plug in numbers like 1.1 or 1.01 or 1.001. Those are numbers that are getting closer and closer to 1 from the right-hand side. These are numbers that are a little bit smaller than 1. These are numbers that are a little bit bigger than 1. And we're going to take each of these numbers and plug them into this function right here to see what we get. So pick one and plug it in and do the computation. Now remember, when you're plugging this in, order of operations matters. So when you put this into your calculator, you want to put parentheses around the numerator. And parentheses around the denominator. Otherwise, order of operations says the division happens before those two subtractions, which is not what you want. So when you get one of those answers, just tell me which x value you used and tell me what you got.
For 0.9, I got 0.52.
0.52. Okay, thank you. Other people?
For 0.99, I got 0.50.
Okay, can you give me a couple more decimal places? So 0.5025,
25.
0.5025. Other people?
For the next one, I got 0.5002.
0.5002, good. And has anybody plugged in any of the values on the right-hand side?
For 1.001, I got 0.49975.
0.49975, good. I'm assuming somebody plugged in 1.1 and got something like 0.48-ish. How about 1.01?
.4975.
0.4975. Okay, great. I think those will do. So you can see what's happening as you're getting closer and closer to the number 1, which we can't plug in. We saw when we plugged that in, we get 0 over 0, that's garbage. But when you plug in numbers closer and closer, so as x approaches the number 1, f of x approaches what number? What number are we getting closer and closer to?
0.5.
0.5, right. 0.5 or 1/2. You can write it however you want. As x approaches 1, f of x approaches 0.5. So let me introduce a notation. We write LIM for limit. The limit as x approaches 1 of this expression, x minus 1 over x squared minus 1 is equal to 0.5 or 1/2, however you want to write it. 0.5 or 1/2. So you read this, limit as x approaches 1 of x minus 1 over x squared minus 1 equals 0.5 or 1/2. So we can't plug in x equals 1, but we can certainly plug in values close to 1. And as we do, we get values closer and closer to 0.5, closer and closer to 1/2. What that means on our picture is that this hole is at height 1/2. As the x values get closer and closer to 1, the y values get closer and closer to 0.5 or 1/2. And even though maybe plugging numbers into your calculator isn't the most fun thing to do in the world, this is a very simple process. You didn't do anything complicated. We just plugged in numbers closer and closer to this number right here. Is everybody with me so far? Is that good? Awesome. Let's see. So we can certainly find limits numerically. If I ask you to find the limit of a function as x gets closer and closer to 3, just plug in numbers that are like 3.1, 3.01, 3.001, so we know what's happening from the right, and 2.9, 2.99, 2.999, numbers that are close to 3 from the left. And when I say left and right, what I mean is on the number line. Let's see if we can do this graphically. let's draw a picture of a function. It's going to take you a little time to copy this function down, so I will do my best to be patient and wait. Sort of drawing in my own graph paper here. So here is a graph of y equals f of x. A slightly more broken up curve than you're used to, more broken up function. It looks like most of you have mostly got that. So let me ask you some questions. Looking at this picture, what is f of 1? You plug in x equals 1. So this is, of course, the x-axis. This is, of course, the y-axis. If you plug in x equals 1, what's the y value according to the picture?
2.
Well, say it again.
2.
2, right? Yeah. So if we stand at x equals 1, we look up or down for a piece of the curve with a closed circle. We see it up here at height 2. So f of 1 equals 2. What is the limit as x goes to 1, as x gets closer and closer to 1 of f of x. So if you plug in values closer and closer to x equals 1, so we're getting closer and closer to x equals 1, what happens to the y values? What are they getting closer and closer to? So we're walking closer and closer to x equals 1. We keep checking these y values, whether we're walking in from the left or the right. What are those y values getting closer and closer to?
-1.
-1, right. As we get closer and closer to x equals 1, as we imagine ourselves a little ant on the x-axis, walking closer and closer to x equals 1 from the left or from the right. The y values get closer and closer to -1. You can see we're getting closer and closer to that open circle at height -1. Is everybody with me so far? Can you read that off the picture? So this is true since as x approaches 1 from the left or the right, the y values approach -1. So they have to approach the same value as you come in from the left or the right for the limit to exist. If they don't approach the same value, then the limit doesn't exist. So were these limits from the left and the right to approach something different, the limit wouldn't exist. Let me ask you now about f of 2. What's the y value if I stand right at 2?
0.
It's 0, because if I stand at 2 looking up and down for my closed circle, I see it right here at 0, my filled in circle. So this is 0. What about the limit as x goes to 2 of f of x? So again, we're going to walk closer and closer to x equals 2 from the left and the right. And we're going to check these y values. What can you tell me about those limits coming in from the left and from the right at x equals 2?
They're not the same.
Yeah, they're not the same. As I come in from the left, I'm getting closer and closer to y equals 0. And as I'm coming in from the right, I'm getting closer and closer to y equals 1, height 1. They're not the same. So this limit does not exist. And we write that so often that we need an abbreviation. We write DNE. We use DNE to mean a limit. We don't use it for a function, we use it for a limit. So you would write DNE next to a limit if the limit doesn't exist, and it certainly doesn't here. What about f of 3? If I stand right at the x value 3, and I look up and down for a piece of the function or for a closed circle, what do you see?
There's a hole.
Yeah, there's nothing there. There's no closed circle. There's a hole in the curve. So this is not defined. So we won't write DNE because we're not talking about a limit here. We'll say not defined. F of 3 is not defined. There's no y value at 3. But if I ask you for the limit as x goes to 3 of f of x, what can you tell me? What's the limit? As you get closer and closer to x equals 3, what's happened to the y values?
2.
Yeah, 2. The y values get closer and closer to 2. So the limit can exist even if the function is not defined there. We saw an example like that in our previous example. If I say, what's f of 4? What is f of 4? Oops. Is there a value of the function of x equals 4? Now it looks like I have a vertical asymptote there, so it's not, there's no value. This is not defined. And right now, I'm just going to say, since we want these limits to be numbers and there is no y value, we're not getting close to any y value, any number, we will say the limit for now as x goes to 4 of f of x does not exist. If some of you are saying, oh, maybe that should equal plus infinity, we'll come back and define that later. So we eventually will say that that limit equals plus infinity, but we don't really have a good definition for that. So for now, we'll just say it's not defined. How about f of 5? What's the value of the function at x equals 5?
One.
Sure is. Yep. If I go to x equals 5, the value of the function is 1. And what about the limit as x goes to 5 of f of x?
There is none.
There is none?
Well, there's no hole.
There's no hole, but as I get closer and closer to x equals 5 and plug in y values, what are they getting closer and closer to?
1.
They're getting closer and closer to 1. You're absolutely right. So just because there's no hole doesn't mean that the limit doesn't exist. All the limit means is as you get close, as x gets closer and closer to whatever number is here, what's happening to the value of f of x? In other words, the y values, if we have a picture like this. How do you feel about this? Is this good? Well, that's basically the entire thrust of the very first section. So we can finish actually a little early today, and we're already working on our calculus. We will continue this next time, and I will see you on Monday.